Welcome back to this particular session. We'll continue our discussion on this airfoil and then wick. And to start with or to begin with, why this particular thing is so important. If you recall that we have talked about different momentum theories, the momentum theories with wick rotation. So thing here is that since your rotor blades or the turbine blades, they are rotating, so there would be some wick because anything which is kind of an the body which is rotating and the any fluid here in this particular case is air passing over that, and then there would be some kind of a flow separation towards the tailing edge, and that generates obviously from the tip also. Because of this rotation, the wake actually forms. Since I mean, even nothing happens, what happens is that with your what do you call if this kind of structure, so if you have this and there are these blades which are rotating, then behind this rotation, and if you have a wind flow like that, so these are the tip, and because of this rotation, this rotor blade tip behind that, there could be a rotation which will come behind that. So wake is an important aspect of it because that plays a very critical role. Because if you have too much of wake, which means I mean that can affect the subsequent turbines if you are talking about cluster and things like that. So so what we want to look at is the first question which comes is that what is wake? You see here, these are the turbines, and behind that this kind of structure. So this is a ship traveling right to left, and you see this structure. This is called wake. So this you can find in nature in multiple places. Okay, nature this exists. So if you talk about the duck swimming in water, you will see this kind of wake. If you see the birds flying in air, you can see this kind of wake. You can see some kind of an wake even the aircraft is flying, and due to that, so you have this kind of wake which is kind of visible in nature in different form. So it just so here this is now let's zoom a bit and try to see, so that the same picture here, we zoom in bit, come close to the or turbine, you could see this. So this is the front row of the or front row of turbine. This is the subsequent row, and you see this is the probably row after that. So if you think in terms of form perspective, the flow this particular turbine is exposed to is clean air, the air which comes on the surface, whatever that is the clean. Then behind this turbine and this turbine, they are under the effect of this turbine. This wake is going to impact this turbine, and similarly the coupled wake of this is going to impact this turbine. So the wake is pretty big in size, and some of the turbines are sitting directly in it. So once you have it, what is going to happen? Effectively, this is not going to give you the optimal power that you expect to extract out from a particular turbine. So maybe the front turbine provide you some kind of an power, but the subsequent turbine would not be able to perform that way. So what one is supposed to have is that clean flow as best possible way is going to is going to hit the turbine, so that now if you zoom further, what you see, the obviously from firm's perspective, the flow at later turbines is not fresh and won't contain as much as energy, which I've been talking about. The later turbine would not be able to produce the energy as you expect. The big primarily reason behind that is that is within the wake or the effect of this first turbine or second turbine. So the third turbine, under the effect of these two, so that's what it won't be able to produce the power as much. And if you look at the individual perspective, so wake limits the extractable power. So that means, in a simple words, if this turbine they are of similar kind, if it exposed to clean air, it can produce, let's say, P1 power, then this should be P2 and this is P3. Obviously, P3 would be way less than P2 than P1. This is what is going to happen because P3 is having an impact of. So, but ideally, what one would expect that P1 should be equivalent to P2 should be equivalent to P3 almost. So that is the ideal situation that all three of them giving. That's what the advantage of the farm. You would kind of, so what you see, the wake is pretty big and some of the turbines are already sitting inside the wake. Now the question comes, what is this wake doing? Okay, so that's something you can see. So obviously there will be some implications which is on lift, angular momentum detour, some experiments that one can see. How does the wake affect wind turbine? Then conceptual way to model the wake, how we practical information to. So that's how. Now coming back, the airfoil that we have already seen, that when the airfoil is within a fluid, when the flow passes over this, obviously you have lift and drag force, which is one is the normal to the flow, other case is the perpendicular to the flow. So that's what you get. Then lift and drag force would allow you to. So here is the one where flow is going around that, and then you have this flow coming, then going out, then there would be reaction force. Now, if you see another perspective, so this is the flow coming in, remains attached here, and then it goes around that. So this is where you see. So what it creates, you get to see some kind of a circulation, not rotation. Okay. So you have some circulation around this particular aerofoil. So when the aerofoil goes through this kind of an inside air, this kind of a flow pattern, so this generates some kind of a circulation. So how do we estimate that? You can estimate in a slightly, simple way. Let's say you say that the whole objective is at rest, then you impulsively start it, you raise the speed up to that point, then you stop impulsively. So this is what it is. So this is a velocity time curve kind of thing. Then for constant lift coefficient, what happens to lift? So the same thing, if I have constant lift coefficient, then what happens to lift? I would have a at rest, impulsively start, impulsively stop. So at the same way, when I impulsively start a lift and that lift remains constant till I impulsively stop it. So this is how you, so then when you look at that airfoil structure, around that circulation would be formed and how the circulation would be there. So when I start impulsively, the circulation is going to be formed, which is bound to that wing or the airfoil. And then when I stop, it comes down. Okay. And what happens to that circulation, that one has to have conservation of angular momentum. So the angular momentum of the flow bound to the wing would also be generated. So what about the conservation of that? So one has to, because this is again something when you have, and this angular momentum would come in picture because your body or the solid is rotating. Okay, so that is there. So now question here is that what part of the flow might be acting to conserve angular momentum? So that is something we have to see. Now we go back and again see the same wake structure. So the wake is a distributed flow. So behind these obstacles, so these are all wake that you see, and these are highly turbulent in nature. Okay. So what is there is an hypothesis which would be possibly that the wake acts to conserve angular momentum. That could be an hypothesis. But yes, one has to showcase and establish that. So now we can see how that can possibly happen. So we have to see hypothetically how would that work. So we'll come back to this particular status of the situation. So the speed we have started impulsively. Accordingly, you get a leap instantaneously generated. Then you have a circulation which is going to. So this is an aerofoil, and it is exposed to a flow. So the flow goes around the aerofoil. So obviously, you have a circulation over there, which is gamma, and then the angular momentum of the flow bound to the wing. Okay. So when I have the same situation, what happens is the angular momentum set into wake at start. So as soon as I impulsively start, speed goes up, lift goes up, circulation start happening, angular momentum set into wake at start. Okay. Then when I stop, then the angular momentum also set into the wake at stop. So this is what we are trying to kind of showing where it is stopping. Yes, some portion, this is impulsively stop. So when I impulsively start, it's going, then impulsively stop. Some portion is also can be a reverse one. So that's where then the circulation set into the wake also at sudden stop. Because obviously, as soon as the flow is stopped or impulsively started flow is stopped, that is also going to happen. So now we can see by some observation that or measurement that how things happen and what happens to that. So you have some 2D experiment, which is an impulsive start. We want to see or we try to answer, is there anything said into wake? So that's the first question that we try to address. So let's say it's a impulsively start. Is anything said into the wake? So we have started impulsively and we want to see if something is setting into the wake. So once we do that, you can see the flow structure like that. You see this, all this graph that we have done, and you can start seeing some structure which is happening and then going. So thing that you get to see, yes, there is something which is setting into the wake. Now, that means if you see the sequence of structure, when we start the system, here is the situation where the flow remains there, it goes. Now impulsively you start, then you start getting these kind of things. So you see this, it goes here, it starts going like that. So there is something which is happening. So now the second question is that is circulation said into the wake? We can see now we have some measurements where the particles are there. So these are the circulation because flow is coming. So there is a circulation. So you see the circulation pattern. Is the circulation setting into the wake. Now, next picture, it shows something is moving out. So then you get another pattern which is going out. So the point is that is circulation set into the wake? The answer is yes. So that means that here, when you impulsively start this flow, the circulation sets into the wake. So that is there. Now more you can look at from the infinite to finite wings. So this is something where you have circulations. These are circulations. Then this is an infinite wing. That means, and if you look at the finite wing, so you can see this cross-sectional area. So the leading edge, there is a circulation, and obviously the lower face is always high pressure, upper face is low pressure. Then here you always you can see at the tip, a trailing edge, there would be circulation. So which you can see that around the wing tips. So both the infinite and finite wing shows some kind of a circulation around that. So is the circulating motion trailing behind wing tips? Now we can look at that through some measurements. It's a 3D measurements, steady level flight. Does the circulation trail behind the wing? You can see the structure which is getting captured. And now next set, you pin this side and this side you can see, let's rotate this side. So essentially what we are trying to do, we try to mimic the situation of the rotor blade and try to see what happens. And this is what you are going to see, that one side if you pin, the other side if you rotate, then the circulating motion trailing along the helical path behind the rotating wing tips. So same thing you get to see in the turbine. So obviously we try to answer the circulation trail behind that. So this picture clearly show the circulation trail behind that. So this is what it shows, and it clearly states that there is another image where clearly shows that the circulation trail behind the wingtips. So, and if you pin one end and allow the other end to rotate, then obviously the circulation going to be there. So that means what is this wake doing? The wake is essentially conserving the angular momentum. So that is what wake is doing. So it's conserving the angular momentum. Okay. Now Second questions what we would like to see. So wake does angular momentum conservation. Now, how does wake affect wind turbine? Now we can see this particular experiments where the rotor blades are rotating in a tunnel, and you see this vortex structure and all these things. What happens? It is going to have some velocity deficit. This is an uniform flow which comes towards the rotating rotor blade, and when it passes, then at the downstream, what you get to see, there is a profile like this. So you have some kind of an velocity deficit, or the wake actually decreases the velocity. So if you see the velocity profile here, so the uniform flow which is approaching to the turbine, and after turbine you get to see this. So the wake decreases the velocity, and this is going to impact your power output, because power is proportional to velocity cube. So once you have less velocity, then it is going to uh, decrease your power as well. Now the question that we have, how does the wake affect an aerofoil? You take a simple airfoil and there is a circulation. So if you see, this is effective velocity, this is apparent or approach velocity, and this is the induced velocity, and there is an angle of attack alpha. Okay, so this again bringing back to that particular, these things, the velocity triangle principle, and we can see. So this is the airfoil where you have effective alpha, induced velocity, and if we put them in, so this is my lift and drag, and that's my resultant force. So this, I mean, purple one is due to the projected according to UE, and the green one is projected according to UA. So there is a slight difference of that, and these differences are called drag induced lift via circulation. So this difference is called, and the other one. So what that tells you, that wake effectively increases the drag. That means, and that is quite natural in that sense, that when you have wake, that there is a velocity reduction, and that velocity reduction is going to impact the power production, and then you will have some effectively the drag increase. Okay. Now, one conceptual way to model the wake is like, we can imagine this following. So simply we imagine that there is an invisible state which is called current, conducted in a structure which is called wire. So these are wire. Then that produces a force field which is electromagnetic field, and then there is a circulation, certain particles. This is magnetic circulation. So that's a correlation one can establish between this, what do you call, electric field and the flow field. So what we could correlate, the current we could correlate with the vorticity. The wire that we say that could be vortex. The electromagnetic field could be pressure field. The magnetic things is the fluid. So the analogy is also pretty similar. In the electromagnetism, you have Poisson equation for electrostatics. So that includes your vector potential with the current density, Ampere's law. But in aerodynamics, this is psi is the vector potential, omega is the vorticity, and obviously this is the definition of vorticity, and flow field is E infinity plus del cross rho. So once you define a circulation as flux of vorticity through surfaces, then you get this. Now, if we extend that similar analogy between this electromagnetism and the aerodynamics, and the Kutta-Joukowski expression says that the lift per unit span is proportional to circulation. So you can get lift, which can be correlated with circulation and the free stream velocity, and you have that. So you bring in that analogy, same analogy in the equation. So there you have the del square psi is minus omega. You have all these definition. So finally the solution would be in format that you have infinity plus this integration. So once somebody is able to do that, then you are able to find out that correlation and then find out the solution. So there is a nice correlation or kind of a connectivity, one-to-one connectivity between the electromagnetic field and the aerodynamic field here. So now you talk about the boundary layer. So you have infinitely far away, then you see this. So there is a solid boundary, then there will be free stream things. So this we have been kind of talking about that. So if the boundary layer is there, this is solid boundary, and close to that, you have no slip boundary condition, and up to certain height, you have the shear gradient is strong. Beyond that, the shear gradient is pretty much negligible. So if you look at the fluid particle here and the fluid particle here, they are having different kind of issues, because here the viscous is related to the viscous shear, but here and it is might be negligible far from the solid bodies. So what you can do, these boundary layer theories and all these things that we have already talked about, that can actually bring some nice situation here. So you remember we are trying to solve this ux equals to u infinity plus this integration. Now we can separate this v into two part. One is within the boundary layer, let's say we marked with the red omega, and the other is the external flow, which is outside the boundary layer. Outside the boundary layer, your viscous effects are negligible. So the point here is that we are trying to kind of demarcate in two components. One is within the boundary layer, where viscous effects are there, and then outside boundary layer. So in boundary layer, external outside the boundary layer, the vorticity is 0. So that drops out from the integral. So it is become ux is infinity. Within boundary layer, that is not 0. So local circulating motion of fluid element due to viscous shear state. So these are potential flow example and things like that. So what you can see, this boundary layer concept actually saves a lot of effort. So here you see there is a boundary layer here, and outside that boundary layer there is no effect. Okay, so what we can do, we just break that into two components in the whole domain and then try to segregate out. So this is precisely what you do. You see the boundary layer formation and then try to mark them. So this is outside boundary layer and this is within boundary layer. So this red shows that within boundary layer, this has to be integrated, and this is outside boundary layer. So the whole solution would be in two component, u infinity plus the boundary layer component, which is required, the non and the outside boundary layer component. So that way, if you segregate that out, that actually gives you an easy solution. And so it discretize omega into vortices, and then points, curves, and lines are present integral. So finally, you get the solution of the LSI field. So what it gives you, that once you outside the body and inside the body, you segregate that out within boundary layer and outside boundary layer, then it is easy to find out the solution. And that is what it is doing. So what we talked about is that the wake, so wake conserves angular momentum, but at the same time, wake decreases the velocity. And now, because of that, you get some induced drag and all these things. So that is something one has to take into consideration while designing this thing. Okay. So with that, we'll talk about other thing in the next session. Thank you.